Bom dia a todos. Vamos dar início ao nono workshop, né, da pós-graduação em Física, tá? E aqui temos a presença de pessoas que representam a universidade, né? Temos aqui a presença do professor Cleane, né, representante da chefia de departamento, né, do coordenador. Temos aqui a presença do professor Paulo Renato, que é o coordenador da nossa pós-graduação em Física, da UFPI. Temos a presença aqui do professor Jefferson, representante da coordenação do centro, né, vice-coordenador, e temos a presença do nosso Lúcio, reitor, né, hoje é o seu último dia de trabalho, aí dei essa missão para ele aqui já passada na abertura do nosso evento, então, professor Arimatea, né, e gostaria de agradecer a todos aí pela presença, tá? Então, vamos fazer aqui a nossa abertura, então vou passar a palavra para o professor Cleane, tá? Para ele dar as boas-vindas, tá? E aí, posteriormente, eu passo a palavra aos demais. Está mutado, Cleane.
Certo, ok. Então, bom dia a todos, né? Com grande satisfação que a gente tem para recebendo. Oi, tá falando? Bom dia.
Não, estamos te ouvindo.
Então, a pauta aqui. Então, a satisfação receber a todos, né, no evento. Espero que esteja com os devidos cuidados, né, a gente tomar devido a essa pandemia. Mas, assim, agradecer a presença de todos, o convite para participar da mesa, né, dessa abertura. Então, o departamento está muito feliz pelo evento que vem sendo tomando, o nono encontro, né, do workshop da pós-graduação em Física, sempre convidando e implementando, né, a questão de novas pessoas com áreas diferentes, para apresentar, para demonstrar um pouco do que vem fazendo. Isso é bom para o curso da graduação, pois estimula, né, a presença, a questão dos alunos verem o que é que pode ser desenvolvido, tanto para os alunos do departamento, quanto de outro, quanto da sociedade de um modo geral, né? Às vezes a gente fica um pouco aquém de demonstrar o que é feito dentro da instituição. Então, o departamento hoje, né, tem buscado, junto com a pós-graduação, sempre tentar desenvolver um pouco mais, e a gente sabe que, queira ou não, a instituição, de um modo geral, ela só se desenvolve a partir do momento que a gente tiver pós-graduações envolvidas em cada departamento, né, e que esses cheguem ao final de abertura, que é fechar o ciclo, que é a abertura de doutorado. Então, felizmente, o departamento, de um modo geral, a gente conseguiu a abertura do doutorado. Estamos iniciando agora a batalha para que mantenha o doutorado de uma forma mais eficiente, bora assim dizer, mais criar um corpo para manter essa pós-graduação aberta de uma forma geral e desenvolver mais a parte de pesquisa de uma geral, que a gente tem que buscar implementar novas áreas, desenvolvimento de novos conhecimentos. Então, é uma grata satisfação. E aí, passo a palavra novamente para o Arani. Então, bom dia a todos e bom evento para todos.
Muito obrigado, Cleane, pelas palavras. Realmente, a pós-graduação realmente ela tem uma grande importância aí no desenvolvimento tanto da própria universidade como do curso e do centro, né? Então, eu vou passar agora a palavra para o professor Paulo Renato, coordenador da pós-graduação, tá? Ele comentar um pouco aí sobre o nosso programa.
Deixa eu só colocar rapidinho aqui 4 slides. Já está aparecendo aí?
Já.
Apareceu?
Sim.
Apareceu, né? Pronto, então,
Sim,
eu vou
sim.
falar rapidinho aqui, concordando aí com o
Só
Cleânio, a
clica no botão
universidade, ela
ocultar.
tem... Ocultar. Só fazendo coro aí com as palavras do Cleânio, a universidade, ela, ela tem vários aspectos e, no nosso caso aqui, a gente tem que ter essa interação entre todas as instâncias, tanto a administração superior, quanto a graduação, quanto a pós-graduação. Então, sempre tem essa comunicação, tem que haver. Então, não é possível você ter uma falta de integração entre esses elementos, né? Então, na graduação e na pós-graduação, a pós-graduação tornando a graduação mais forte e a graduação fornecendo os alunos com boa formação para ir para a pós-graduação. Então, nós temos aqui o nosso primeiro slide sobre o nosso nono workshop, os palestrantes. Então, eu queria falar só alguns números, só fazer um breve histórico aqui da fundação do nosso mestrado, em que foi fundado em 2008 com a nota 3, e até o momento nós já tivemos mais de 100 mestres titulados, 109 para ser exato, no começo do ano, porque eu tirei esses dados no começo do ano. A gente já teve titulação de mais alguns, então deve estar aí por volta de 115, mais ou menos isso. Então, de 2017 a 2019, de 2010 a 2012, foram 27 mestres, o curso era nota 3, de 2013 a 2016, foram 50 mestres, o curso já era nota 4, porém apenas com mestrado, e em 2017 e 2019, 32 mestres titulados, e a gente já tinha conseguido aqui em 2019 o doutorado. Então, o doutorado foi criado em 2019, com a aquisição da nota 4 já, na época do mestrado nota 4, e a gente conseguiu o doutorado. Obviamente, a gente não tem nenhum doutor ainda titulado, e nós temos hoje 19 professores no corpo da pós-graduação, 17 professores permanentes, um colaborador e um professor visitante. Atualmente, nós temos 15 alunos de mestrado e 8 de doutorado. E as inscrições para o próximo semestre estão abertas, serão 4 vagas para o mestrado e 3 para o doutorado. As inscrições vão até dia 2 de dezembro. Então, nós temos uma vasta gama de linhas de pesquisa, desde semicondutores, sistemas complexos, propriedades térmicas, temos ótica não linear, que é uma área já que é tradicional, e transição de fase também, nanomateriais, que é uma área que está em alta com fins para a tecnologia, física de polímeros e a área de teoria quântica de campos. Então, basicamente era isso que eu queria falar, dos números, que nós tivemos uma sessão relativamente rápida, creio eu, e desde 2008 para cá, e era o nosso sonho realmente chegar no doutorado, e nós conseguimos chegar. E agora, como o professor Ani falou, o professor Cleânio, consolidar esse programa, né? Primeiro consolidar, para depois a gente pensar em voos mais altos. Então, queria agradecer a fala.
Obrigado, professor Paulo Renato, pelas palavras. Então, agora eu passo a palavra para o professor Jefferson, tá? Para representante da direção do Centro, né, de Ciência e Natureza, o vice-coordenador, né? Ou é vice-chefe, não sei, é vice-coordenador.
Vice-diretor.
Diretor.
É vice-diretor, verdade.
Então, muito bom dia a todos e a todas. Primeiro, agradecer o convite e parabenizar o Departamento de Física, o curso de pós-graduação em Física, tanto a nível de mestrado e doutorado, que vem se destacando há muito tempo aí dentro da nossa universidade do estado do Piauí. Eu digo que o Departamento de Física, o mestrado, o doutorado, ele está muito em estágio muito parecido ao da matemática, né? Nós também recentemente conseguimos o nosso doutorado. Com o apoio da administração, nós tivemos um crescimento muito rápido. E agora o grande desafio, tanto para o Departamento de Física quanto para o Departamento de Matemática, é justamente consolidar esses programas que começaram tão bem, pelo menos na nossa avaliação. Então, não é de agora que o Departamento de Física, junto com o programa de pós-graduação, eles fomentam muitos eventos, né? Inclusive, é uma característica nos últimos 4 anos do Centro de Ciência da Natureza. mas, em geral, tanto os cursos de graduação como de pós-graduação vem realizando muitos eventos, e a gente aqui na direção vem, na medida do possível, tentando ajudar sempre naquilo que for preciso, naquilo que for necessário, para que a gente consiga engrandecer os nossos programas de pós-graduação. Eu tenho uma relação muito boa com a física, né? Até por ser da matemática, então eu sou meio suspeito para falar da qualidade dos cursos, da qualidade dos professores, do engajamento de todos, até porque a gente está muito próximo, né? São departamentos vizinhos. Então, no mais, eu quero parabenizar a organização do evento. Esse momento de pandemia é um momento singular, né? Nunca antes visto. Então, são coisas que vêm para ficar, né? Então, o evento, apesar de a gente gostar de estar todos juntos num determinado ambiente, num auditório lotado, para a gente poder confraternizar e estudar física, no caso, agora a gente está aqui à distância, né? Mas, por outro lado, isso é uma coisa boa, porque também aproximou muito as pessoas. Hoje a gente pode ter vários professores, vários pesquisadores e vários alunos agora com essa realidade virtual. É claro que a gente torce para que logo, logo isso passe, para que a gente possa novamente estar junto, interagindo, discutindo matemática, discutindo física, porém é o que a gente tem no momento e eu acho que essa é a saída, inclusive, para reduzir custos, né? Que é a grande pergunta de todo gestor, né? Como reduzir custos num momento tão complicado como esse? A saída virtual é lógico que nunca vai substituir a presencial, mas, de fato, a virtual veio para ficar. Então, no mais, agradecer novamente ao convite. Sempre que chamado, o Centro de Ciência da Natureza está à disposição para ajudar qualquer curso do centro e qualquer curso também fora do centro, dentro da universidade. E muito obrigado e bom dia para todos.
Obrigado, Gerson, pelas palavras, tá? E agora eu passo a palavra para o nosso magnífico reitor, tá? Gostaria de agradecer, eu sei que sua agenda está lotada, né? Último dia, mas por sua presença, tá? Então, eu passo a palavra para você.
Obrigado, Ironi, obrigado pelo convite. Quero cumprimentar o professor Jefferson, o Cleânio, Paulo Roberto, o professor Ironi, claro, a todos que estão nos acompanhando, a todos que fazem o programa de graduação em Física. Dizer que é um prazer estar participando da abertura deste evento, sendo hoje o meu último dia de mandato, né? Amanhã já teremos um novo reitor, e feliz de estar encerrando o mandato com a sensação do dever cumprido. Nós estamos aqui no evento de pós-graduação, e na nossa gestão, nós passamos de 6 cursos de doutorado para 21. Então, só esse número já mostra, né, a evolução da universidade na nossa gestão, né? Então, quase quadruplicamos o número de programas de cursos de doutorado na nossa universidade. E esse crescimento, claro, deve-se, em grande parte, ao empenho do corpo docente de cada departamento, de cada curso, mas também, em parte, às ações da administração superior. Nós criamos a figura do professor visitante, que não havia na Universidade Federal, não tínhamos nenhum professor visitante em nenhum programa. Nós criamos a Bolsa de Produtividade. Somente a UFP, a única universidade federal que concede Bolsa de Produtividade a seus pesquisadores com recursos próprios. Não há nenhuma outra. Então, uma ação importante para incentivar os nossos pesquisadores. E essa concessão dessa bolsa, além de incentivar os nossos pesquisadores a concorrer ao edital, a produzir para concorrer, também incentiva a concorrer aos editais dos órgãos de fomento, porque para participar do nosso edital é preciso que ele tenha concorrido aos editais de órgãos de fomento. E muitos bolsistas de produtividade UF se tornaram bolsistas CNPq. Então, realmente um apoio importantíssimo. Nós lançamos o edital também de apoio à publicação científica. Os pesquisadores que publicam recebem um valor para compensar o gasto com a publicação, que hoje em dia praticamente toda revista cobra, né? Há algum tempo atrás, não. As grandes revistas não cobravam, só aquelas revistas que o cara não conseguia publicar numa grande revista, pagava para publicar em outra. Mas hoje não, hoje já é mais ou menos uma prática comum de todas as revistas cobrar pelas publicações. Tivemos também o edital de incentivo ao intercâmbio com universidades estrangeiras, né? O professor nosso poderia passar até 15 dias numa universidade estrangeira, ou trazer um professor de lá até aqui. Isso aconteceu com diversos professores da universidade, também com orçamento nosso. O apoio à infraestrutura dos programas também, diversos prédios de pós-graduação foram construídos. Claro que tinha uma parcela da FINEP, mas se não tivesse a contrapartida da universidade, não aconteceria. A aquisição de equipamentos, a questão do investimento em TI, que foi muito grande, né? O firewall que nós conseguimos adquirir para a universidade, moderníssimo, né? A instalação do Wi-Fi em toda a universidade, o aumento da velocidade. Quando nós assumimos os campos fora de sede, a velocidade de conexão era 4 megas. 4. Hoje, eles têm 2 links de 200. E aqui em Teresina, 1 giga. Então, estou feliz de estar saindo da gestão, né, com sensação de dever cumprido e com apoio, né, à pós-graduação. Porque eu entendo que uma universidade não existe se não tiver uma pesquisa de qualidade e uma pós-graduação de qualidade. A pós-graduação e a pesquisa refletem na qualidade do ensino de graduação, sem dúvida nenhuma. Isso é um grande diferencial das universidades públicas. O fato de possuir pós-graduação, de possuir pesquisa, faz com que seus cursos de graduação tenham uma melhor qualidade. Então, quero aqui parabenizar a todos que fazem o Departamento de Física, pelo trabalho realizado, pela dedicação, pelo empenho. Nós hoje formamos um número de profissionais licenciados ou bacharéis em Física maior do que a média das universidades federais, né? Isso graças ao empenho da equipe, sem dúvida nenhuma, que Física é uma área que forma poucos profissionais, mas na nossa universidade tem um número maior do que a média das universidades federais, e isso, sem dúvida nenhuma, é em razão do empenho, da dedicação de vocês. Nós conseguimos também melhorar a qualificação do corpo docente da nossa universidade, nós assumimos, nós tínhamos 600 doutores, mais que dobramos esse número, né, professores do nosso departamento, e também, inclusive, quantitativamente, tivemos um acréscimo no quadro de pessoal de muitos de docentes no departamento. Então, mais uma vez, parabéns a todos vocês, e deixar aqui meu agradecimento pela parceria, pela contribuição de toda a comunidade acadêmica. Hoje aqui quero agradecer em especial ao Departamento de Física, na nossa gestão durante esses 8 anos. Eu costumo dizer que durante esses 8 anos, a UFP foi administrada pela comunidade acadêmica. Uma gestão democrática, ouvindo a comunidade antes de tomar as decisões. E sempre tomando decisões do interesse da instituição, da academia, da comunidade. Nunca focado em interesses pessoais. As demandas que nos eram apresentadas, elas eram avaliadas pela qualidade, pela relevância, nunca pelo autor da demanda. Tá? Então, sempre foi dessa forma que nós agimos. Espero que continue assim, para que a nossa universidade continue crescendo. Então, muito obrigado a todos vocês pelo apoio que tivemos em todos esses anos e parabéns pelo trabalho realizado e boa sorte nesse evento, né? Um evento que está acontecendo agora de forma remota, como disse o Jefferson, nós gostaríamos muito de estarmos nos encontrando presencialmente, infelizmente esse momento não permite, mas eu acredito que mesmo passada a pandemia, como foi dito pelo Jefferson, nós vamos continuar ainda tendo um formato híbrido, né? Com algumas participações presenciais e outras com outras participações remota. Né? Isso, por um lado, traz a vantagem de você poder contar com professores de diversas instituições de outros países sem muito custo. Então, eu acho que isso aí é uma vantagem que veio por conta da situação que nós vivemos. Quer dizer, algumas coisas vieram para ficar. Então, quero encerrar aqui minhas palavras, já que eu tenho uma reunião agora às 9 horas. Mais uma vez, meus agradecimentos, meus parabéns e desejando pleno êxito e mais um workshop da pós-graduação em Física. Muito obrigado.
Bom, gostaria de agradecer as palavras do Magnífico, tá? E agradecer aí a todos pela presença, tá? Então, damos início ao nosso nono workshop da pós-graduação em Física, tá? E peço licença a vocês agora para desfazer a mesa, tá? Porque aí temos agora uma palestra com o Sandro e Sorella. Obrigado a todos. Bom, dando continuidade ao nosso evento, tá? Depois aqui dessa abertura, né, com os representantes aqui das diferentes esferas da universidade, tá? Gostaria de convidar o Natanael professor da UFRJ, colaborador do nosso programa de pós-graduação, tá? Que vai mediar a apresentação do professor Sandro Sorella. Também gostaria de convidar o professor Sandro Sorella. Agradecer pelo convite. Grazie mille.
Grazie a voi.
Okay. Sandro, I have just to say some few words in Portuguese, okay?
Okay. Then you have to teach me how to share the screen and things like that, right?
Okay, because I believe in the bottom of your screen you have the possibility to share the screen.
Share screen. Click and share screen.
But I have to say just a few words before you start to share the screen, okay?
Yeah.
Okay, of course.
Primeiramente, agradecer ao Eroni, né, pela oportunidade pelo convite, a oportunidade de mostrar o que a gente está fazendo aqui. Eu particularmente fico muito feliz pelo convite, porque eu sou prata da casa, então fui ex-aluno aí, tanto de graduação como de pós-graduação, fiz mestrado aí. E, diga-se de passagem, eu estive no primeiro workshop, certo? Então, eu estava lá no primeiro, como aluno ainda de mestrado, e apresentei no segundo workshop, né? Então, em particular, para mim, é um prazer enorme estar aqui, e eu tenho certeza que esse workshop desse ano vai ser um sucesso. Só para dar um recado para os ouvintes, esse seminário vai ser dado em inglês, né, por conta do nosso convidado. Mas vocês podem fazer perguntas, aqueles que não se sentirem à vontade para fazerem questionamentos em inglês, vocês podem fazer em português, que eu estou aqui acompanhando aqui o chat aqui do lado, e aí vocês podem fazer a pergunta assim, em português, que eu traduzo para o inglês. Mas podem também fazer no inglês, enfim, vocês escolhem. E sinto-se à vontade para perguntar. Eu acho que essa é uma grande oportunidade de aprender também, né? Eu enquanto aluno aí, no primeiro e no segundo workshop, aprendi bastante. Então, vamos agora mudar para o inglês. Aroni, você tem mais alguma coisa a adicionar?
Não, pode ficar com a palavra. Tá bom, obrigado.
Obrigado. Então, so let's start with our talk with our invited speaker, Professor Sandro Sorella. I will just do a very short introduction about our invited speaker. Okay, Professor Sorella is a full professor here in Sissa, in Italy, Trieste, Italy. And he is certainly one of the most important scientists in the field of strongly correlated systems. In particular, I would like to mention that he has done very important contributions for the development of state-of-the-art numerical methods. For instance, he was the one that first developed the zero temperature approach for the auxiliary field, one method that is vastly used in the field. And he also conducted many other developments, for instance, on variational and diffusion Monte Carlo, and many other techniques, exact diagonalization, and many other numerical techniques. Part of this knowledge about Monte Carlo mailing are now summarized in this book, which Professor Sorella is the author. This book is Quantum Monte Carlo Approaches for Correlated Systems, that is now published in Cambridge Press, so you can find it on Amazon or any other website. And over the past years, Professor Sorella also has conducted some research in the field of the electronic structure, with contributions on graphene, and recently on the phase diagram of the hydrogen chain, a paper that now is published in PRX, I believe. As a result of this recent research on electronic structure, he now is releasing one open source package called Turbo RVB, in which you can use variational and diffusion Monte Carlo for electronic structure simulations. So I believe this is what Professor Sorella will present today for us, this new developments that he has done in this field. And it's a great pleasure having you here, Professor. So you have around 40 or 45 minutes to your presentation. And the questions, I believe the questions will be done in the chat, and then I tell you, okay? So you can start.
Okay, thank you very much for this very kind and probably exhaustive introduction. So I don't have to talk anything else because you have said everything. So I will try to share the screen. Come would like to have this computer screen? Open system. I have to open. I think we have this problem. But now I have to restart because this is the first time I use Google Chrome for this. And I have to restart because this Mac want to have. Can you wait a few minutes?
Like 2 minutes?
Yeah, I think I have to restart the system.
Okay.
Quit now.
No problem. We can wait like 5 minutes. Okay.
Meu computador aqui tá. É que a minha internet aqui tá travando.
Eu tenho. O público tá bom. Nós temos agora mais ou menos 72 pessoas, então tem muita gente. Que bom. Maravilha.
Aí eu aviso ao pessoal que infelizmente aconteceu esse problema, porque a gente pressupôs que o professor já tinha. Mas acontece que tem MacBook, acaba dando esse probleminha. Ele vai ter que iniciar lá o Chrome. Aí já voltou, ó. Deixa ele só.
Problema de.
Coloca ele, Matheus, por favor.
What happens? Share your screen, your entire screen. Okay. And why does not want to share now? You don't see my screen, right?
Not yet.
What do you want to do? Share? No. And this not. Share screen. Don't show this thing again. I have a window that I cannot. Share your screen. Share. Application window. This one. Okay. Oh, now you can see this, right?
For me, it's not appearing. Okay. Now I share it. Okay, good.
Now you see my first slide.
Yes.
Sorry for the delay. Huh?
No problem.
Each time you have a new application to use, I have to do this part. I'm sorry about that. So I hope I will be in time. So this is a great pleasure for me to open this workshop, and I will discuss about recent and even not recent advances in quantum Monte Carlo in the group I'm leading in Sissa. So this is the outline of my talk. Basically, I want to describe variational Monte Carlo and to convince you that is a reasonable technique that is based essentially on a very simple ansatz that I called generally Jastrow mean field. So you can see my mouse, right? Here. Can you see me? Nathanael, you see?
I do not see your mouse.
You don't see my mouse. So okay. No. So this means that I cannot use the mouse. So just a mean field, and with this wave function, we started a long time ago to study strongly correlated system on a lattice, and I will show that since this is very successful on this system, we can generalize this approach to solve to give a very good approximation of the ground state on realistic systems. And the main point is that we not only have a more accurate description, but we can have access to phases that are not described by the near field. For instance, the Mott insulator, to say something, a system that according to band theory would be a metal, with this approach can be described even if it is a Mott insulator. So this is the web page. Below you will see the web page where all this project is so far available. And the main point of this toolkit is that since we believe that we can change qualitatively our mean field description of matter, the main point is to optimize the variational wave function in presence of a correlation term that I call quite generically Jastrow, and this change the physics and goes in the right direction. This project started, the motivation to do this project dated back to 20 years ago, and basically we see that the state of the art of electronic structure density functional theory, even nowadays, but the main point is that even at that time there was a plethora of functional, and some function is always found that provide a good description of some material, but at that time also, and even now, nothing has changed much. You can always ask whether this is a way to do ab initio calculation. So try to predict material properties without knowing nothing else than the Schrödinger equation, or if it is a way to fit the experiments. If we want to do instead ab initio, I believe we have to go back to a wave function-based approach that is certainly systematically improvable. And the point is that the wave function approach, even if it is not exact, we have a criteria, a guidance to understand whether an approximation is better or worse. We just look at the variational energy, and if it is lower, it is better. We are still waiting for an exact solution of the Schrödinger equation for a system for a large number of electrons. I can mention density matrix renormalizations group, tensor wave technique, recently also machine learning wave function based approach, or design problem solution for the quantum Monte Carlo, and in quantum chemistry post-Hartree Fock methods. But none of these is able to give the exact answer so far. So the question was, why don't we try to do this variational Monte Carlo, that is a simple-minded approach to the ground state of an Hamiltonian, but for a realistic system with a full electron-electron Coulomb interaction. So this, I have to mention several collaborators during these years. So the first one is Michele Casula. We started this project in his PhD thesis. Then came Claudio Attaccalite, Spano, a very nice postdoc, D'Agrada, a very good developer of some part of the code, and recently also we acquired a very good postdoc, like thanks to the Japanese collaboration, Nagano Kosuke, that is doing a lot of effort to make more accessible this code. I am fortunate to have a lot of support from Japan, Italy, and recently also we got a grant from the European community. T-Rex was a name that I was suggesting, fortunately was luck that it was get. This TR is just the first, the main letter of the turbo RVB code. They don't know that this was the reason, but it's probably a good advertisement for my code. So that let me explain in one slide. This is variation of Monte Carlo. The nice thing is simple. So we don't understand so far what machine learning means, but we know that human learning is an important thing. And based on human learning, we can propose a guess of what could be the ground state of a system. And in my point of view, we write this as a mean field wave function, the most generic mean field that you can think of, that we decorate with the correlation term. Of course, this variational wave function depends on several parameters that I indicate by alpha in these slides. And the question is that based on the variational principle, the most accurate guess that we can have is obtained by minimizing the energy. But you know, as if you don't have any correlation term, you can do this calculation on the back of the envelope or with your laptop. You can do the R3FOC, even if it is complicated. But if you put the correlation, this calculation cannot be done easily. But you have to rely on Monte Carlo. What is Monte Carlo? Well, basically, what you have to think, we have a black box machine that is able you to provide the expectation value of any wave function, any of a class of wave function, because as long as this wave function can be computed given a configuration where the electron position and spin are given. So if I can do the calculation, even if the wave function is correlated in a computational time, I can generate configuration according to this probability distribution, and then instead of computing this calculation with a multidimensional integral that is probably very complicated, I have only to sample a random variable that is called the local energy. That is a much cheaper calculation of this. For typical wave function, we can compute the local energy in a reasonable computational effort. So this task is very simple. It's proportional. The computational time is only proportional to the number of samples that you give. And of course, the error bar decreases like the inverse square root by the central limit theorem, by the inverse square root of the number of samples that you do. So you can achieve basically, if you have a good computer, the accuracy that you like on the expectation value on any correlated wave function of this form. So the times left, what is more important is how to optimize this expectation value, and this will be dealt in a few slides later. But let me just emphasize that this what is the physical motivation to deal with this wave function. The motivation dates back to the theory of Linus Pauling that introduced the resonance-valence bond concept to describe the chemical bond. Basically, when you put two atoms very close together, and you have a valence electron on each atom, you like to form a singlet bond of these two valence electrons. That is this simple equation that I have written here. The idea is that if you have a complicated system, you can propose to pair electron valence electrons in several different ways. The historical, the most quoted example is the benzene molecule. You know, the benzene is composed by 6 carbon and 6 hydrogen. Each carbon has 4 valence electrons, but 3 of them are completely saturated in the plane because you have 3 sp2 orbitals, that one of them joins with the hydrogen electrons here, and the other two join with the other carbon. And so this means that at the end of the story, on each carbon, only one valence p zeta orbital is left, and this has to be occupied by only one valence electron, because all the other are in the plane, essentially. And you are in a situation of strong correlation, because you can take two valence electrons in a single bond, form a valence bond, but then you have to pay attention to what you are doing in the other. If you think a bit, so you have an hexagonal structure, so you can pair two neighboring carbon with a valence bond with this wave function, but you cannot pair another bond nearby, because otherwise you will have two electrons on the same carbon site, and you will pay a big Coulomb repulsion. So the two valence bond configuration that you can build on the two main are the so-called Cagoulé valence bond structure. And the reason, the point of Paul is that I have not to put only one of these, otherwise I break the rotational symmetry of the molecule, but I have to do the coherent superposition of these two valence bond structure. I gain energy, and this is called resonance valence bond energy. Basically, the theory was very nice because as a physical interpretation was very successful, but you can understand that if you increase the complexity of the system, the number of valence bonds that even here, if you want to derive, I have written more valence bond configuration in this. For each of these, you have to do some kind of mean field Slater determinant calculation. So the calculation increase with the number of valence bond. So the idea instead that was taken by Anderson several years ago was that this kind of resonating valence bond structure can be obtained in a much cheaper way. Well, the original motivation was to explain high temperature superconductors, and so in which electrons are paired naturally with opposite momentum and opposite spin in the famous BCS wave function. But the BCS wave function is not good for an insulator. So what happens to describe the Mott insulator when you have no holes in the system is to put a Gutzwiller projector that is nothing but a special case of the Jastrow factor that I mentioned in the introduction. If you put the Jastrow factor, you can see that, for instance, in the most famous example, in the triangular lattice, you take all the pairs that can be come out from a BCS wave function, and you draw in your lattice, in your triangular lattice. So you see that there are several of these pairs, and the effect of the Gutzwiller projector is that you cannot have two valence bonds connecting the same site, as we have seen in the benzene molecule. And this is a much cheaper formulation, because what you need to know is to do a mean field, and then by Monte Carlo employ the Jastrow correlation, which means that the calculation is done with only a single mean field ansatz. So that's why it's advantageous. I did in this project the most general RVB wave function of the form proposed by Phil Anderson. So the most general mean field ansatz is of course the ground state of the most general mean field Hamiltonian that is defined by the most general quadratic form of fermion operator. So the most general one has to have a generalized hopping that depends on, that is long range, it depends on the spins in a non-trivial way. So you can break the symmetry, for instance, in an antiferromagnet or ferromagnetic system. And the most general BCS gap function that, of course, You have seen in the way superconductor has a special symmetry, and usually in BCS superconductor you pair only opposite spin, but you can also have triplet superconductivity, you know, in which you pair also parallel spin, etc., etc. So this is the most general mean field, and of course the mean field can be easily worked out, and believe me, the most general ground state of the mean field Hamiltonian can be written in this form, like the exponential of a pairing function. This is basically the solution of this mean field equation for 2 electrons, and you exponentiate it. So this is is the information of the 2 electron solution in the most general case. Electrons are paired within. This is in fact called the pairing function. And on top of that, you apply the most general Jastrow factor, that is a function, again, of 2 electron operators that depends only on the density on each side. So this Jastrow factor is easy in some sense because it's diagonal in the configuration where the electron position and spins are given. So this becomes a number on each of these configuration X that I sample with Monte Carlo. And the only thing that you have to take into account that there has to be a general dependence in U and F. So how to generalize the wave function on a realistic Hamiltonian? Well, this is it's just intuitive. There is no difference. We have to work in fixed quantization that is simpler, for instance. So basically, this pairing function is a function of 2 electrons that, by the Pauli principle, has to be antisymmetric, and that's it. Once you have this, you can, and you have a system of n particles, you can put n and half pairs with these 2 electrons wave functions. But the important and difficult part is that since the particles are indistinguishable and they follow the Fermi statistic, you have to put on top of that an antisymmetrization over all particle permutation. This could appear a very horrible task computationally because the number of perturbations is n factorial, so it's basically almost impossible to enumerate them for n equal 20. But some algebra comes in our help, and essentially the evaluation of this exact allowed physical wave function, because it's a perfectly antisymmetric software, amounts only to the calculation of the Pfaffian of a matrix that is defined in terms of this pairing function that is only n by n. And this is, you have to accept, is a standard routine that costs a polynomial cost. N cube flops, you can do the calculation. So you can work out even thousands or several thousand of electrons without, in modern supercomputer, without any problem. This was realized long time ago and was written in this paper. So we can provide now, you can understand what is the full ab initio electronic Hamiltonian that we want to describe. We are condensed matter physics, we are lucky. This is written in atomic unit, so the Hamiltonian can be written in one line. And we assume Born-Oppenheimer approximation, so the atomic position are fixed, whereas the wave function should depend on all the electrons and spins of the electrons. And the point is that I want to convince you that we can apply Monte Carlo is that basically this Jastrow mean field wave function can be calculated once we give the configuration of electrons and spins. In fact, as I have told you, the determinantal part, that is the most generic mean field wave function, can be calculated by computing a Pfaffian of a matrix. And the Jastrow part, once you have the electron position, amounts to a number of operations that is trivial. This summation is n square operation, where n is the number of electrons. So this can be computed, and so we can do generally Monte Carlo evaluation of the expectation value of this wave function over the true Hamiltonian with a method that is polynomial in time. So you can do thousands of electrons. There are, it is important in the following of this talk to just take in mind these acronyms, because this is the most general formulation, but you can go down with the more restrictive formulation in your MIFID, obviously. This is, we don't allow any pairing between parallel spin, and we take the most generic function that depends on two coordinates, and this is called the unrestricted geminal antisymmetrized pairing function that will be denoted here with this acronym, just of antisymmetrized geminal power unrestricted. Then we can restore the spin symmetry, because this was the original Pauling formulation, in which we assume that a chemical bond is only a singlet bond between two valence electrons, and this is called JIGP. And then we can further discrete, go down with a restriction, and we limit our wave function to be a fixed rank. That means that it is fully described by a set of molecular orbitals, and you can easily expect that when you have this restriction, this is a particular restriction of our geminal, our Pfaffian function, you get, after antisymmetrization, the standard Slater determinants. This means that we can go back to the standard formulation of the mean field that you use, for instance, in density functional theory. And this also means that if we exploit the largest variational freedom when we go from down to up, and to the previous case that was called JPF, which is the most general one, we have always necessarily to decrease the energy of the system. This is just by the variational system. So this is the notation. Why we have to take this effort? Well, I have to go back to the most simple lattice Hamiltonian, that is the Hubbard Hamiltonian, that is described only by one parameter, U over T. And you know that if you are not able to put the correlation in your wave function, so you work only with the mean field, and you are trying to get the D-wave superconductivity from this Hamiltonian with the mean field, you put in your BCS mean field wave function this kind of pairing, you optimize the variational parameter, and you discover that you cannot have any superconductivity. Instead, if you optimize these two, the correlation term and the mean field part all together, you discovered a qualitative new effect that is given and is provided only by strong correlation, that the Hubbard model can indeed sustain a D-wave superconducting ground state at finite doping. This case is U equal T equal 8 at 10% doping, if I remember correctly. But this is the main point. With the optimization of both the correlated part and the mean field part, we can have a qualitative new description of the physics of a system. I want to summarize what is known, because you can think this is quite arbitrary ansatz. You can define several other ansatz, tensor network or whatever. This is a simple ansatz. You generalize in all possible way your mean field, and you put the most general possible just of correlation that is defined in configuration space. So what is known is that, for instance, if you do the one-dimensional system, the prototype model for a metal is the Tomonaga-Lattinger model. This model can be exactly written in this form as a just from mean field, provided you put as a mean field plane wave Slater determinant as a just-off, a long-range just-off. This was shown analytically, so there is no question about that. And so you mean that, you know, metals in one-dimensional state are rather peculiar because they don't have a quasi-particle, finite quasi-particle weight. You have not a Fermi jump in the momentum distribution. If you put this just-off mean field picture, you can represent also this very, very important property of matter, one-dimensional conductors. So another important point, if you do the spin wave theory of quantum antiferromagnet, you discovered that for large spin, so when the spin wave becomes exact, the spin wave theory becomes exact, the ground state wave function can be written essentially as a just-off, a spin just-off, applied to a mean field that is now the standard nil state, where all the spin, nearest neighbor spin have opposite spin. So this is also a nice exercise, but qualitatively important is to emphasize that we can describe Mott insulators. So for instance, in one dimension, if you take the Hubbard model half filling, it is known by the extra solution to be a Mott insulator. You can take a Fermi gas, which is a metal, apply a just-off factor, and turn a metal to an insulator just by this kind of answer. So you can really find new phases of matter if you open your mind to these answers. And the question is whether this exhausts at the end all possible phases of matter. In my opinion, yes, I have not found any anomalous or non-conventional effect that cannot be dealt within these answers. For instance, it is interesting, I don't want to, that there is an extra solution of a model, a strongly correlated model, the Kitaev model, very famous. So this is the model in which it is possible to show that the ground state is a spin liquid. So this work is very important because it shows that the spin liquids are systems that at zero temperature do not have any kind of order parameter. This is like the most wonderful representation of a resonating valence bond state. And this, if you carefully inspect the ground state of this model, you can show that this is just a Gutzwiller projected Pfaffian wave function. So the one that is incorporated in this mean field structure. So also this spin liquid state can be parameterized by this wave function. Well, I will show the superconductivity. In some sense, also the Lafton wave function can be interpreted by the Lafton mean field, and there are several other types. So let me show the successful example that I was working for several years. Is the TJ model, is the strong correlated version of the Hubbard model. You take large U limit, you go back to a coupling that is not large, but 40 square over U, and the model is this, and the strong correlation is that the hopping now is done with the constraint that you cannot you work in a Hilbert space where there are no doubly occupied sites. The wave function of this is very trivial and is of the form of a just-off mean field. The mean field is the BCS because we assume that the ground state of this system has the wave superconductivity as in a strongly correlated system. May happen, not necessarily happens. And the just-off is particularly simple. You just have to avoid from this mean field configuration that do not satisfy the constraint. This is very simple. The mean field Hamiltonian contains only one variational parameter that is proportional to the gap of the system. And indeed, if you optimize this variational parameter in presence of this strong correlation constraint, you discover that when you go to the Mott insulator, that would mean x equals 0, this variational parameter increases. a variational parameter in a strongly correlated wave function does not necessarily means that is related to the critical temperature, like in conventional BCS superconductivity, because when you are at half filling, there is a strong correlation constraint that does not allow you to have superconductivity, and you have actually an insulator. So this is amazing, because this kind of effect is indeed realized experimentally when you do photoemission experiment. You just measure that the gap at the so-called pi hot momenta, which is pi 0. You see that this value is larger at pi 0. Is actually of this form, increases when you go when you get closer to the multi-insulator. Instead, if you compute the actual order parameter, the off-diagonal long-range order, you discover that this has a maximum at the optimal doping, as you would expect. The order parameter is like that, and this was found several years ago with this variational approach. 14 years later, there was a big effort. I don't know if you have followed this tensor network and do the exact solution of all the models. They have done a big progress. Actually, they were able, with all this effort, to go beyond our variational energy that were obtained with this Jastrow mean field with some correction that is called the fixed node approximation. But anyway, essentially they get better energy. This is probably not a factor of 2 or 3 better, because this is the extreme added data. But most importantly, they want to claim that they were getting something that was qualitatively different, because the order parameter of the wave type was very small, whereas another order parameter that is related to the antiferromagnetic long-range order that in this system displays in a non-uniform way that is called stripe, was much larger. But however, I was just careful enough. I put the number of our prediction that was 14 years ago, and basically they agree. They agree not only qualitatively, but also quantitatively. So there is only a slight overestimation in our approach, assuming that they are exact. Within an error bar, I don't see any difference. And you see that basically at the claim that we have done, where they also claim that there is no stripe, basically we agree. And so this we can say that at most we can say that the stripes is not clear, because we have not found the stripes with the variational approach in the TJ model, but certainly that the fact that the strongly correlated model can sustain the wave superconductivity is established, because 2 independent methods at a different period of time have obtained almost the same result. This is amazing, I would say. And this is the most beautiful confirmation that the variational Monte Carlo can anticipate the events. So somehow is interesting for this. And this is the main point of my dissertation, is that maybe nowadays we have also other methods, machine learning wave function proposed by Troyer and Carleo, with a larger follow-up papers, and progress on tensor network. But nevertheless, it is clear that for realistic simulation, they have still to work a lot, several years, before they can go further. Instead, we have, as anticipated, we have a method that can improve almost automatically our best variational wave function, that is so-called the fixed node approximation within the diffusion Monte Carlo. This method allows not only to include 2-electron correlation, because the Jastrow that we have implemented is the most general 2-electron correlation function that is in the exponential, but you can include all many body correlation you want. You can correlate 3 electrons, 4 electrons, 5 electrons, And automatically, by clicking a button, you can improve the best variational wave function that you can think of, with the restriction that this just of factor correlation has to be positive. We cannot change the sign of our mean field ansatz. The big problem comes when we try to put to evaluate. So the wave function is defined by these two functions. One is included in the Jasto, and one in the Pfaffian wave function. We took the policy of quantum chemistry calculation, and we expand a function of two variables in a given basis, in a given atomic basis. This indicates an orbital which is of the Gaussian form that is centered on an atomic position that are called A and B here. And all the variational parameters now are two big matrices that can be quite large. For instance, you take a system of 1,000 electrons, even if you put one orbital for each atom, you have a 1,000 by 1,000, 1 million variational parameters. So this is a big effort because the problem is related to optimize several parameters. And that's why it took a lot of time. This is the picture of the field is turbo RVB. All the code is done in Fortran, and you can guess what is the format of this project. And we have to do a minimization of several parameters. Let me show how it's difficult at that period to imagine to optimize several parameters, because even in a paper of 2000s by a very important person like Masao Okada, my colleague, in order to optimize two parameters, what one has to do to optimize first given parameter as a function of delta, look where is the minimum, you have the error bar, you are not even sure, and then you change the second parameter. So it was a real mess with Monte Carlo to optimize even two parameters. But there was a very big step forward at the end of the millennium, fortunately, obtained by myself and within the neural network computation. The first step was to understand that the energy derivative of our variational Monte Carlo calculation can be done by computing the covariance of two random variables. One of them we have already seen is the local energy, but you have to compute only the logarithmic derivative of the wave function with respect to the variational parameter that you want. We have seen that this is computable, so of course it's computable also the derivative. By doing, and we know how to do the Monte Carlo, we sample configuration according to the probability, and so we compute all the derivative. Even if we have 1,000 parameters, we can apply gradient descent. But unfortunately, gradient descent is too slow. So this, if we follow the direction of the gradient, and it was immediately realized in that period by introducing either the Fisher information matrix, either what is called the stochastic reconfiguration, that is an improper name, I believe is better Fisher information matrix. You compute a quantity, a matrix that is obtained for free, because if you want to compute the derivative, you have to compute these operators with this random variable, and the covariance of this random variable defines this matrix. So you are and it was realized that there are several reasons why this should work better. You can go to the literature, and basically, if you precondition your gradient with this matrix, you go much faster. Let me give you a recent example. This was a recent work done by people that work with machine learning based variational wave function. There are several parameters, and even though there are methods that are more popular in machine learning community, when you are trying to do variational Monte Carlo, you want to have a very, very good accurate solution. So in machine learning, if you want to beat with the chase game, you don't need to go to the exact minimum of your function. You can also stay here, and you don't get this is a good minimum. But if you want to do accurate quantum chemistry calculation, you have to go to the real minimum. So basically, natural gradient or stochastic reconfiguration is almost unavoidable. Let me show now at the end. Unfortunately, I am exceeding my time, but I think I have 10 minutes more because of this problem. And this is a few examples. One of these is that very simple. We have 4 hydrogen as a function of the vertical and horizontal direction. The point is that when the system they are far apart, they prefer to form a valence bond in the vertical direction. When they are close, then they prefer to have a valence bond in the horizontal direction. Of course, you can guess what happens when you are in the square situation. You want to have a resonance valence bond that oscillates between these two. If you have a stick in the single determinant picture, you cannot describe this system. If instead you are using the just-on mean field wave function, you can determine this the ground state of this wave function with 4 digits. I don't know if you do the diffusion Monte Carlo, and you can beat also multi-determinant scheme. Ken Jordan believed that this cannot be done without using 1 million determinant. Instead, you can do with a just-on mean field, with 1 mean field, not several. So this means, and what about the Buffian? I want to give you only one more example that is very simple. This was introduced several years ago before us, I have to say. There are several papers, but they didn't exploit all the variational freedom because they were limited with, they were not giving the general variational freedom that we are able to do with our approach. And so basically this was depressing. The main thing that we have to understand when we apply why we need to use the Pfaffian wave function, because if we have a system of 2 atoms in which the spin of the atom is pointing one direction in one atom and in the other, and we apply a Jastrow factor that can change the SZ in the same quantization axis where the atom spin atom is directed, then we cannot do nothing to this kind of wave function, because this wave function multiplied by the Jastrow remain the same wave function. Instead, if we rotate the quantization axis of our mean field with respect to the Jastrow quantization axis, the Jastrow becomes important. And as I have told you, in a quantum antiferromagnet, this is what you have to do. You have to apply a Jastrow perpendicular to the quantization axis. But when you do in our mean field this rotation, we go from a single slated determinant to a Pfaffian. And so we have to use the Pfaffian, the most general Pfaffian function. What happens? This is very interesting. So basically, in our approach, we can turn off the triplet correlation with this unrestricted geminal, but in that case, the Jastrow has not the right quantization axis. If instead we use the most general case, the JPF, you see that we get an order of magnitude improvement in the description of the binding energy of the molecule. This is very important because we can get really very good, very accurate result at the chemical accuracy, essentially, the red point. But the most remarkable thing is that the improvement that we get with the Pfaffian that was not given before. It is amazing that our result is competitive not only with the standard multi-configuration interaction, multi-determinant. So you can take billion of determinant and you have this kind of accuracy. You see, in 2 cases over 3, we have a better accuracy than this multi-determinant approach, and we are very close anyway to the exact result. Not only, but we can beat also in accuracy the most recent machine learning based wave function that is this cross here, Fermi-net case. So this is very successful, and the physical effect is given by the spin fluctuation energy gain that we have obtained by releasing our wave function. it is important that with this mean field approach, we have a physical interpretation of our cases, because what happens, we can measure directly the spin moment around each atom as a function of the distance. And what is the difference with respect to the nitrogen, which is a standard triple bond? Is that the spin is not screened by the covalent bond. And indeed, this means that the C2 molecule acquires an extra binding, so what we have gained by incorporating the spin fluctuation, not because there is a strange fourth bond picture that is still under discussion around the quantum chemistry community, but just because for this simple fact, the C2 is the smallest nil state in nature. So this means that this is exactly an antiferromagnetic system, and the extra bonding that makes this molecule peculiar is just due to the spin fluctuations. So I want to show in 1 minute the last advances otherwise, and one of them is the calculation of forces in quantum Monte Carlo. We have the possibility with this approach to understand what is the pairing function in a complicated system like iron compounds. This was the blue are negative points of the pairing function, the plus are positive, and you see that this we can call for experiment if this is true. But the most important achievement is that we can compute now forces, not only energy, thanks to algorithmic differentiation. And we can, with the computational times that is roughly 3 times of the computational time that for which we compute the energy, we can compute all the atomic forces in a big system like that. So that is much more information you can understand. And this means that even thanks to this recent development, we can do also molecular dynamics. This was a work done by Michele Casula and collaborators. And not only, we can include also quantum effect on protons. Quantum effect that seems to be important in this ab initio molecular dynamics based on quantum Monte Carlo forces, because you see that the proton, thanks to quantum fluctuation, can fluctuate from one water molecule to the other. And this is an important effect that is captured by our wave function. I want to finish because I have exceeded, I'm sorry, the time, and more information is obtained in this website. And parallel to this, in our group, we are also developing a strategy also to deal with lattice model, and one of the leaders is Nathanael Costa in our group. And this is and all the information, further information, you are welcome to visit our website. Thank you for your attention, and sorry for the little delay.
Thank you, Professor Sorella. Let me see. We have some questions here. Let me see. The first one is from David Alencar. The question is, I believe you see, can classical Monte Carlo algorithms like Metropolis be precise to study electronic structure in a general way? So I probably understood that he's asking if a classical approach can be used instead of a quantum one.
Oh, I mean, I don't know if I have understood the question well. Of course, if you want to say that I can try to fit my Born-Oppenheimer energy surface with a classical potential, and this is actually a very important project that we also have in our group. You can use machine learning way to do this fit. And of course, now, many people is trying to do this with density functional theory. You can do much better with quantum Monte Carlo because the energy surface, as I have shown, is better. And then you can apply, once you have the potential, you can apply classical Monte Carlo on this potential, and you can get the realistic simulation with the accuracy of quantum Monte Carlo, with a very cheap calculation, with classical Monte Carlo, molecular dynamics, what you want.
I see.
I don't know if it is.
I have a question. To the best of my knowledge, calculations of determining superconductivity in DFT, using DFT, is quite difficult, right?
Yes, it's very difficult. There is a Gross has done trying to do several works on this, but
yes.
As a matter of fact, is not able to. I mean, it works in system that are electron phonon, but is not able to explain high temperature superconductivity.
But it seems that using variational Monte Carlo, it is almost one free parameter to you, right? So you get your parameter or superconducting parameter like without any effort.
Yeah, the problem is that in principle this can be done. I mean, this is already possible in this Turbo RBB toolkit. It's a lot of calculation, because in order to show that the system is superconductor, you have to do the finite size scaling. So you have to be able to reach very large supercell, and this is this is at present the difficulty. So you need a huge supercomputer, but fortunately, there are several improvements in high performance supercomputing calculation, and nowadays probably the calculation is possible. So for instance, to do a 6x6 copper oxide plane by ab initio simulation, and so you can do the finite size scaling from 2x2x2 to 6x6x6 and see what happens.
I see. I have one more question. Sorry.
No problem.
Can you tell us some words about spin orbit coupling? So is it possible to you analyze it? Because it seems that spin orbit is just one two particle term, right? So a single particle term. Sorry.
Yeah, yeah. There is not possible at present in Turbo. There is Lubos Mitas that is working on spin orbit coupling with Monte Carlo, and I think, of course, it's possible, and it's probably worth to do. I think you are alluding to the topological insulator,
yes,
things like that, right? Yes, of course, it would be nice to see this effect also by realistic calculation.
Okay, so let's see if we have more questions here. No, we don't. Okay, if you don't have more questions, I would like to just ask you just few more words about the possible use of quantum Monte Carlo for ab initio with the advent of quantum computation in the future.
But this is a competition, because if quantum computer works, you don't need to do this approach.
Okay.
Quantum computing itself is a stochastic approach, basically. Okay. So you will certainly not do Monte Carlo on top of that.
Okay.
You have to repeat several times the same experiment, which is basically what you...
So it doesn't improve too much.
Oh, it's a competitive approach in the sense that they claim that they will be able to solve one day without the Schrödinger equation, if you want, without having, well, I'm not probably not precise in this. They could have also ansatz, because they can provide variational ansatz within quantum computations. But the point is that the variational Monte Carlo is based on the fact that with the classical machines we can do this integral, multidimensional integral, with the restriction that the sign has to be positive.
Okay.
And so we do half of the job. To do the full job, so to sample exactly also the sign, we have to rely on quantum computation, if they will be able to do one day.
Okay.
And this is not possible with classical machine to solve the same problem, right?
Okay. So thank you very much, Professor Sorella. I believe there is no more questions here. Then we appreciate a lot your talk. It was a very good one. Like you gave us.
I'm sorry that I don't
very good introduction.
Because
yes.
I suppose that maybe
you gave us a very good introduction about quantum mechanics and RV resonance bond. So it was very pedagogical, even for the students that are here. Okay, thank you very much.
Bye
Have a good day. Ciao.
Stop sharing, so leave studio.
So now, nós voltamos aí com a Eroni. Obrigado, Eroni.
Obrigado. Eu dei um delayzinho aqui, ia falar. Então, assim, eu vou deixar, só para o pessoal dar frequência, eu vou deixar a frequência no comentário, tá? Qualquer coisa a gente coloca no grupo, deixar um tempinho, tá? E gostaria de agradecer aí, Natália, pela condução aí da palestra do professor Sorella, né? Você é da casa, né? E aí avisar o pessoal que 10 daqui a pouco, daqui uns 7 minutos, a gente começa a outra palestra, só que vai ser em outro link. Então, vocês podem ficar no canal, que vai aparecer ao vivo, tá? E eu vou pedir aí para o pessoal da organização passar esse link, tá? Então, vou encerrar aqui a transmissão e já começa no outro link, tá? Obrigado a todos. Eu espero vocês lá no outro link, que vai ter a palestra do professor Michael Cabreira e da professora Isabel Cristina, né? O Michael Cabreira da UFPE e o Isabel Cristina da PUC do Rio, tá? Então, até daqui a pouco.